Good day to all of you. Welcome to my online electrical engineering review and tutorial channel. So we will discuss today the problems on AC generation or generation of AC voltages. Okay, before anything else, if you want to know the problems that I will discuss today, just hit the link on the subscription tab on the video on this video, and you can see the link there, and then hit the link, and then you will be transferred to a drive. Okay, so this is more on G drive or Google Drive, and then from there you have the main problems as well as the supplementary problems of this lesson. Okay, let's move forward to problem solving. So problem number 1, I will read the problem first. A sinusoidal voltage has a maximum value of 100 volts. We need to find the effective RMS value in volts. So we already described root mean square, but another term for root mean square is effective value. Okay, so effective value. So from this given, we already have the maximum value, but before we attack the maximum value, you need to know where's the maximum value here. This is the maximum value EM and negative EM for the negative cycle. So you have here 100 volts. We already also described and derived from our last meeting the root mean square value of a sinusoidal waveform. So the answer there is EM all over square root of 2, or 1 over square root of 2 is simply on decimal terms 0.707. And hence, multiplying 0.707 by 100, the answer to this problem, a very simple problem, just to have an idea or application of the root mean square, 70.7 volts. So, HPIPS problem. Okay, let's move forward to another interesting problem. Another interesting problem is to convert phasors to sinusoid by using a very, very useful formula that we will describe at problem number 2. Okay. Let's read the problem first, and this is a former board problem. The current in an AC circuit has an equation of I is equal to 20 sine omega t plus 30 degree. We need to find the complex expression in amperes. So, we need to have the given first. Now, if you can still recall what we have described from the basic principle, that you want to get an instantaneous value of current and voltage, you need to know the maximum value here, the magnitude of the maximum value of the current, sine omega t, the argument. But you have the displacement will be dependent if the signal with respect to reference is lagging or leading. So therefore, you have plus or minus angle theta, and that angle is already described from the basic principle. Go to the basic principle. I've already described a lagging or leading condition of a sinusoid. Now, in this problem, it is positive. So it's evidently, it is a leading condition at plus 30 degree. Okay, now, we need to get the complex expression in terms of I. Now, the so-called complex expression here is the so-called phasor. Okay, now this is the right time, okay, to introduce a phasor. But we will review this one when we go to power system. A phasor is a complex entity that has what? A magnitude and a direction part. Bar angle, direction part. So it means it has a form like this with an arrow sign. If I have an arrow sign here, it means you're considering a phasor expression. A phasor expression has a magnitude of the current or voltage. This is a flexible formula. It can be either be voltage or current. Okay, so this is small letter V, this is VM, capital V, and V here. Okay, so the difference between these two is, in the phasor form, you have here the magnitude of the current and the angle. So the angle here is direction. It means direction or displacement. Okay, so this is in terms of magnitude. Okay, please take note the I here and the IM here is different. The I here must be in root mean square, which means, as we have mentioned, to get the root mean square value of a current or voltage is depends on maximum divided by square root of 2, 0.707. This is root mean square, and this value here at the I, the magnitude of the current here, must be in maximum or peak-to-peak value. So that's the difference between these two I's here. And the angle here is the same. This is the displacement angle. They're the same. But this one, your I, is a time domain. This is in a frequency domain. This is the difference between the two. This is a sinusoid. So sinusoid is in terms of time, with respect to time. When you say phasor, with respect to frequency. So a phasor with respect to frequency domain, the sinusoid is with respect to time. So it means you can convert from time domain to frequency domain. So the complex expression here means it must be in the phasor form or complex form. Okay. You can have a little bit of readings on complex numbers, and it is invented by Charles Prometheus Steinmetz. Okay, so you can search Google, or I think there will be another lesson from here in terms of phasor or complex numbers. But anyway, but just a recall, this is just a refresher course that you can convert in either way, sinusoid and phasor. Sinusoid, time domain, phasor, frequency domain. Always remember that. Okay, in this form, we can have this form here, wherein I, with the direction part of phasor form, is equal to I RMS bar angle plus or minus theta. Okay, in this case, you already have this in the time domain because this is a smaller I, 20 sine omega t plus 30, and this 20 here is a maximum value. So how can you convert it to a phasor value? There's a root mean square, just divide by square root of 2. So therefore, that's the meaning of that. There's a square root of 2 here, okay, because it must be in RMS form. Okay, bar angle theta I, which is that angle 30 degree. Now, you will have this one in a polar form. Okay, now you can have this one in a complex entity. Complex entity must be, okay, in a complex form, rectangular form. So when you say complex rectangular form, so it means this one can be converted to Ix plus J Iy in complex form. Okay, you have your calculator there how to convert a polar to rectangular. So this will be in terms of your calculator. Converting a polar to rectangular form, this is your Ix and this is your Jiy. So the complex expression answer for this problem is 12.24 plus J 7.07 degree amperes. Okay, let's solve some problems again on AC generation. So before we do that, let's read the problem first. Okay, problem number 3. The voltage in a circuit is given by an equation in terms of instantaneous voltage as 100 sine omega t. The omega is 314 plus 60 degree volt. We need to find the period in seconds. Okay, in this case, we need to get the period in seconds here. So let us have first the given. This is the instantaneous voltage E. And that is the omega t. Matic, the omega here is 314 radian per second. And this is the angle theta. So it means we can solve the problem already by having the omega is equal to 2 pi f, and f is 1 all over t. Just recall what we have described on period. The period is the inverse of the frequency. And thus, you have 2 pi f, 314 is the omega, and then 2 pi 1 all over t, and then rearranging the equation, t is equal to 2 pi all over 314. The answer is 0.02 seconds. Very, very simple problem. So as you can see, I have a column here so that we can go forward now to number 4. So number 4, let's read the problem first. A sinusoidal voltage source as a maximum value appears at an interval of 10 milliseconds. What is the frequency? Okay. Now, the keyword here is the interval of 10 milliseconds. The maximum peaks occurs at an interval of 10 milliseconds. So, the only way to do this, or to solve this, is you need to draw the signal first, the sinusoidal signal. Okay, so this is the sinusoidal signal, and you already know where is the peaks here. So this is the peak of the waveform, and they have an interval of 10 milliseconds. Now, since this is sinusoidal and it's very self-explanatory that they have the same area, 5 or 10 milliseconds, so you have 5 milliseconds at the right and you have 5 milliseconds at the left as well. Simply because you have the same positive area and the negative area here, or the cycle. Okay, so this is 10 milliseconds, so it's clear you have 5 here and you have 5 as well from the origin, or 0. And this is the omega t here, or argument. Okay, since we already have an idea, okay, by equation here, 2 times 10 milliseconds, so you have 20 milliseconds. Frequency is 1 all over t, so f all over 20 milliseconds. The answer is 50 hertz. Very simple problems that explains the sinusoidal waveform. Hello and good day to all of you. Now, we will discuss and continue on problem number 5 for the problems on AC generation. So, let us read the problem first. An alternating current of a maximum value of 20 amperes lags the reference voltage by 30 degrees. What is the magnitude of the current 2 milliseconds after the current wave will cross the omega t axis or argument going to the positive direction? Okay, to understand problem number 5, you need to have the basic fundamentals first. So go back to the last lesson that we already described what is a lagging and a leading condition. When you say lagging, last to show, and when you say leading, first to show, with respect to reference. Okay, what I did here is I draw first the reference curve. The reference curve here is this voltage, because the current will be respect to the reference, which is your voltage E, or the smaller e here, or instantaneous voltage E. Now, it is also mentioned that the current will lag 30 degrees from the reference. So, as we have already mentioned, so this is this curve here is a lagging curve, which is last to show with respect to reference. And also one thing as well, it is indicated that the current curve will be 2 milliseconds ahead as it crosses the reference curve. So it means if this is the starting point with a 30-degree angle, so you can convert radians to degree, and this is the 2 millisecond as it crosses the reference voltage. So let's recall our equation. So we have this equation from the last problem that Im will be sine omega t, but it depends on the angle displacement if this is lag or lead. Now it is lagging, so it's clear that it's negative 30 and there's no frequency. So for this will be our main assumption if the omega is 2 pi f and if you have a frequency of 60 hertz. Okay, that omega is approximately 377 radian per second. But if this is a 50 hertz, your omega here is approximately 214. Okay, so it dependent on the frequency, and our equation for omega here is 2 pi f. So this is omega t, 377 t minus 30 degree. And Im is the maximum value, which is 20 on the peak. Now, we can now solve the problem, the instantaneous current. So this is 377 and t is 2 milliseconds. And you can see here, this is degree. Now, the answer here is radian, so you need to convert it to degree by multiplying it by 180 all over pi. The answer for this problem is simply 4.56 amperes. Okay, let's move forward to another interesting problem where in the practical applications of the formulas for the average value from the previous lesson, or previous slide rather, we have here problem number 5. So this is the problem number 6 rather. This is problem number 6. Oops, sorry. Okay, an alternating current of a sinusoidal waveform has an amplitude of 15 amperes. What will be the average current at a frequency of 60 Hz? So, we need to draw the sinusoidal waveform first. And we have here 15 amperes. And then you have the whole waveform. It's not mentioned. Okay, the x-axis here. But definitely, we can have this one as an assumption of pi and 2 pi period respectively. But here our main goal is to get the I average. So how can you get the I average? We already described this one from our previous lesson, that I average will be equal to 0.637 of the maximum value, or 2 all over pi. So just substitute the maximum value 15 here, 2 all over pi times 15. The answer is 9.6 amperes. A very, very, very simple problem